Hello everyone, I am Chen from Microsoft 365. Today I will talk about NetPanel, the traffic measurement system of Exchange Online service. This is a collaboration work between Microsoft 365 and Microsoft Research. First, let me introduce Exchange Service. Exchange Online is a cloud-based messaging platform that delivers email, calendar, contacts, and tasks. Exchange Online spreads its services across hundreds of thousands of machines worldwide. From functionality perspective, it is composed of thousands of components. Each component is a module that performs a specific function as an entire or part of a process. Typical examples in our service include email delivery, data replication, and different kinds of access protocols, such as Mealiffe for desktop, OVA for web client, and POP3 for mobile. To serve customers, these components work together and therefore generate huge traffic across data centers. The long-haul traffic flow that crosses data centers costs Exchange hundreds of millions of dollars per year. These traffic flows should be carefully monitored. A small bug could raise the network bill by millions of dollars per year. NetPanel aims to catch such code regression and assist in analyzing traffic usage to reduce network costs. To give a sense of how request flows in Exchange, here is an example of a user reading email from his or her mailbox. Let's say Bob sent an email to Alice, and Alice wants to read her email. There are 4 steps. First, Alice's client sends a request to the closest Exchange front-end machine. Exchange front-end machines are Layer 7 proxies to help route requests to the back-end machines that actually hold customers' mailboxes. To find the correct back-end machine, front-end servers may need the help from Active Directory machines, which hold users' metadata to find a back-end machine that may know the answer. In step 3, the FE will query that back-end machine for which back-end machine holds Alice's mailbox. And in step 4, it will route the actual request to Alice's mailbox. In some cases, all these machines involved and user clients are in different locations, and each step will generate a long-haul traffic flow. Given the background, NetPanel has 3 design considerations. First, NetPanel needs to provide component-level measurement. The primary goal of NetPanel is cost reduction. In order to drive such kind of effort, we need to assign dollars to people. Each component is owned by one engineer team. We need to get their cost clear to motivate them to take actions. But why component, not process? Back to the previous example, in step 4, when front-end server sends requests to back-end servers in another location, it has to go through another front-end proxy in the same location as the back-end machine. So, when we use process as the traffic owner, all these long-haul traffic flows belong to the proxy, but the traffic may actually belong to different access protocols. Second, the daily data size has to be small, and with our current data service should be in gigabytes. This hard limit is because that to get the insight of their network traffic, engineers have to analyze traffic patterns over weeks of data. Data queries should be returned within minutes. However, IPFIX, the Network Traffic Measurement Protocol, generates more than 10 terabytes of raw data per day. The existing compression algorithms could compress the data size to roughly 10%, but it still couldn't satisfy our requirement. Third, NetPanel has to consume few production resources. Exchange provides very high SLA to its customers, so for every single component, the CPU consumption and disk usage are restricted. Now, let's talk about the design of NetPanel. NetPanel consists of two pipelines, one for data processing. The other is a built-in data validation pipeline. It takes three measurement inputs. IPFIX data are collected by call routers, which sample the traffic flows according to 5 tuples. Event tracing for Windows is a Windows system event collector. We can use it to get network events and keep the process information for network traffic. We further consume application logs. These logs are owned by different engineer teams for debugging incidents. They record request-specific information, such as request and response sizes, and can tell which component owns the request. For ETW collectors, we only collect the records for the top K ports. We'll explain why we do this later. For data processing, we cannot do a direct join for these data sources because each of them is at least in terabytes or even petabytes per day. Instead, we do feature translation, data split, and aggregation. One of the heaviest dimensions in our data is IP address, because Exchange holds hundreds of thousands of machines, and each machine has a unique IP address. Also, an IP address itself doesn't provide valuable information, so we translate it into locations and server roles. This reduces our data size from trillions of IP pairs to millions of feature pairs. Another heavy dimension in our data is port. As is well known, there are more than 60,000 ports on our machine, and most of the ports are ephemeral ports used by the client. We use data split and aggregation to break the pair relationship and aggregate on one side. This also pops up well-known service ports, and thus greatly reducing the data size. In addition to data processing, we also built a data validation pipeline. The data validation pipeline ensures that we can rely on the accuracy of the measurement to make important business decisions. The key idea is to cross-validate ETW data and IPFIX data. The IPFIX spikes could be recovered provided the sampling rate. Based on law of large numbers, we selected a pair of machines that continuously send a large amount of traffic for the experiment and obtained the shown figure. The IPFIX traffic size could match with that from ETW. So we directly select the top 1,000 machine pairs that send the most traffic in a day for data validation. We have deployed NetPanel for more than 1 year in Exchange. First, we'll share some production insights, which further strengthen our design. Then we introduce some case studies to show how we use NetPanel to reduce network costs. We have identified 2 stable production insights. The traffic distribution for cloud applications is top-heavy. Specifically, we have observed that in a half-month interval, the top 10 ports consistently account for over 94% of the total traffic. Furthermore, we found that for these top ports, the top 5 components are responsible for the majority of the traffic. For port A, the top 5 components take up more than 70% of the traffic, while the 6th largest component and beyond only takes up less than 5%. For port B, a single component takes up to 94% of the traffic. This distribution observation greatly reduced our cost reduction effort. We share some cases on how we leverage NetPanel to save costs. The first case is a traffic optimization case. Because Exchange is a very large organization, we cannot guarantee that everyone is on the same page. In this case, there is an internal service that mistakenly uses an endpoint without our routing optimization. We found it because the long-haul traffic from BE to a port on FE is much larger than expected. So we used the component table to further dig in and get the component name. The long-haul traffic to that port was reduced by 20% after the fix. The second case is about legacy discovery. Cloud applications are evolving very rapidly. Changes come and go every day. It is hard to verify that all legacy services are retired. Microsoft has finished the migration of traffic to port C to traffic to port D. So the initial traffic distribution looks surprising to us. And we found that there is a legacy service still sending traffic to port C. After removing it, the distribution of traffic to port C dropped to 4%. The third case is anomaly detection. An engineer accidentally changed log uploading compression algorithm to an older version. The decrease in compression rate led to an increase in data volume and hit the throttling limit of log center. However, the retry mechanism in the component kept sending data. This resulted in nearly quadrupling the peak traffic. After rolling back, the traffic drops back. The last usage of NetPanel we are going to share is one feature validation. Microsoft has marked its background traffic to have lower priority during congestion with DSCP tag. However, this function is not supported by some newly deployed devices. We found this by observing that some of the low priority traffic are classified as high priority in NetPanel. Altogether, NetPanel has helped save tens of millions of dollars per year. Finally, we provide a brief overhead evaluation. IPFIX has been there for traffic management. Application logs is also available in the system for debugging instance. So the extra overhead for NetPanel is the in-production ETW resource consumption and the outside production data computation and storage cost. Because of the port filters added to ETW, we achieved a less than 1% increase in CPU and disk I/O usage. Compared with raw ETW collector, we saved more than 99% of the CPU and disk I/O. For outside production data storage, the data size is reduced by more than tens of thousands of times. The daily required calculation time is around several hours, with less than 0.01% of our computation resource. It takes tens of seconds to respond to a user query about 60 days of data. To conclude, component-level measurement is needed to drive the cost-saving effort for a cloud application developed by a large number of teams. With the observation that heavy hitters are stable in Exchange, NetPanel achieves it through leveraging IPFIX, ETW, and application log. These data sources are in terabytes or petabytes per day. It uses feature translation, data split, and data aggregation to reduce the data size. NetPanel has been in Exchange production environment for more than 1 year and has helped us save tens of millions of dollars. Thank you so much for listening.